Hi guys, today what we want to learn about is something called the kinetic molecular theory. Now the KMT, as it's sometimes called, actually makes sense. If you think about the breaking down of this word, Mr. Dmitrowicz, kinetic, what does that word mean?
It's motion.
Motion. Molecular.
Molecules.
So it's a theory about molecules that move. Right? Think of this world, all right? And it's particularly gases, that there's tiny little gas particles, and we've talked about this in previous segments, that they're constantly moving. And that's basically the idea that they're always constantly moving. So that's for a gas. If I was to draw a picture of gas, right, we've already done this before, they're moving like this. But for a liquid, it's a little bit different for a liquid. Are they moving?
Yeah, everything's moving around. It's this kind of the trippy thing, because when we look at this calculator, for example, you don't think to yourself, ooh, but the molecules in here, if we were to zoom in here.
Dude, you're saying the molecules are moving.
Yeah, every molecule is moving.
Right, and even here in the hand sanitizer, we have a liquid, and what's going on with the liquids is they're moving. Now, it's maybe easier for me to think about this moving and this moving. Wait a second, you're crazy. Are you drunk? I mean, does this? You're saying that this is moving?
At a molecular level, it's kind of cool because the gas particles, we have no doubt, because they just like zoom all around the room. They're completely not linked to each other. Liquids, they're moving, but they're kind of like just holding on to each other, right? Solids, they're locked in tight, but all the molecules, they're kind of just vibrating with each other.
Think like a spring, and they're back and forth and back and forth and back and forth. And actually, the way you know that they are actually moving is probably when you made your breakfast this morning. Maybe you made some eggs, or you heated up some water for your tea or your coffee or whatever. But you know that when you take a pan that's cold and you put it on a stove and you turn your stove on, if you touch that pan after it's been on for a time, you will burn your hand. What's the difference between a hot pan and a cold pan?
It's how quickly the molecules are moving.
Oh, so it's not just how hot it is.
No.
It's actually the fact that the molecules, they're moving like this when it's cold, and they're like this when they are
Old person dance.
hot.
I'll spare you.
I better stop. So the kinetic molecular theory says, so wait a second, we've kind of introduced a new thing. The temperature's something going on there.
Yeah, and the reality is we're speaking specifically to gases, and if you take a look here, there's 4 points about gases, and we'll talk about those in class. But this can actually apply to everything, and temperature has everything to do with this.
So okay, so wait a second. If I increase the temperature, then I have more kinetic molecular energy, right? So how does that work? Is there some kind of equation?
Yeah, there's an equation that looks like this, and it's kinetic energy, Ke, we're clever that way, equals 3/2 RT. Now, this is a scary looking equation, but let me remind you of 2 things here. This R is a constant, which you don't really need to be aware of. But anytime you have 2 things that are on opposite sides of the equation, they're directly proportional to each other. So these are constant. This is directly proportional to this, which means what?
If you increase the temperature, you will increase the kinetic energy. But if you double the temperature, you'll double the kinetic energy.
Correct.
Now, we should talk about, an interesting thing is about temperature, is that we have to work with a new unit of temperature that you're probably not familiar with. It's called the Kelvin scale. So what's up with the Kelvin scale?
Well, in our regular Celsius and Fahrenheit, we have negative values and positive values, agree?
All right, it could be negative, like I lived in Chicago and it was negative 30 degrees.
Yeah, I live in Canada, so negative 3 million, right?
Yeah.
That's impossible, but yeah, it can get really cold. The idea that the kinetic energy, which is the motion of particles, is impacted by temperature means this. If I lower the temperature, lower and lower and
Well,
lower.
they're going to get slower and slower and slower. So wait a second, at a certain point, if they get super crazy slow, they'd stop.
Yep. And so
They can only go, remember we said gas particles going 1,000 miles an hour, but what if they're going 0 miles an hour?
You know, there's a special condition for that. And we say that at that point, when all molecules stop, that's how we define the Kelvin scale. And we said that is called 0 Kelvin, and it has a special name. What do we call that?
It's called absolute zero.
Oh.
Right there. So absolute zero is the coldest possible temperature where all molecular motion ceases. So if that's the 0, not okay, but 0, and by the way, you don't put a degree sign.
Yeah,
It's
they're
kind of
really,
like-
really finicky about that.
Yeah,
They
yeah.
hate
So
degrees.
it's 0 Kelvin and K is for Kelvin. And how do we convert Kelvin to Celsius?
Well, let's talk about Celsius first of all. Whatever our Celsius temperature is, because that's the one we've been using most of the time. If we add 273, and I'll get all fancy on this, 273.15, we end up with a Kelvin temperature.
Okay, so that's the equation. If I know the Celsius, so if it's 0 degrees outside, which is 32 Fahrenheit, right? The freezing point of water, it's 273 Kelvin. Okay,
Yeah, but what if it's 20 degrees outside?
Well, you'd add 20 to the 273, so 293.
So we got to be careful here, because when we talk about this relationship where if we double the temperature, we double the kinetic energy, we're referring to Kelvin temperature, not to Celsius. For example.
So you maybe watched the news one day and they said, hey, the temperature went from 40 degrees this morning to 80 degrees. And then the weatherman or weatherwoman says, the temperature doubled. It didn't double, because it's not the Kelvin temperature that doubled. The Fahrenheit scale doubled. It's probably gone up like 2%, honestly, 3%. It's not a huge jump. So you can't, if you double the temperature, let's say it's 273, which is freezing temperature, it goes to 520 something.
546.
546. That's above the boiling point of water. All life would cease. It would be horrid.
Yeah.
If you double the temperature, it all would be bad.
True story.
Yeah. So you're gonna have to learn how to convert these, and you're gonna see why this is important when we do some like experiments and some gas laws. That's important that whenever you do temperature, always, 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 you must be what?
In Kelvin.
In Kelvin.
So, Mr. Bergmann, I'm Canadian, so I'm completely comfortable with the Celsius system, as is pretty much the entire world, but those of us here in America are holding on to the English system. Can you kind of give us a relationship between what the temperatures are?
Yeah, we know Fahrenheit. We know that if it's like 100 degrees outside, that's crazy hot, right?
Yeah.
Super hot, humid day here in Houston. We don't like 100 degrees. But in the Celsius scale, it's based upon water. 0 degrees Celsius, right? 0 degrees Celsius equals the freezing point of water. So that's 32 Fahrenheit. And 100 degrees Celsius is the boiling point of water. And you know that is 212 Fahrenheit. So just to kind of give you a perspective, your body temperature is like 37 degrees Fahrenheit, which is 98.6 Fahrenheit. So this give you kind of a perspective. So if it's 37 degrees outside Celsius, it's a hot day. It's uncomfortable.
We used to get to like 40 would be like.
But a really beautiful day, like a 70-degree day, I believe is, I want to say 22 Celsius, somewhere in that ballpark. So it's a much smaller number setup, because it turns out that a Celsius degree is about twice as big as a Fahrenheit degree.
There's one last thing before we go, and if you take a look at the kinetic molecular theory, we made some assumptions about gases. Now, we talked about just the idea of kinetic energy versus temperature, but there's some other points that we're going to go over in class. One of the things you need to be aware of is we made two assumptions that aren't true. We lied to you a little bit. And as we did before with atomic theory, we lied to you a little bit, and then we lied to you a little bit less. There are two lies we're going to tell you right now. One, we're going to say that every single gas molecule, they're so small that we don't have to worry about their volume. So when we're measuring the amount of space in a room, we don't have to subtract how much gas is occupying that, which kind of makes our problems a little bit easier. The second thing is this: we pretend that gas molecules have no forces of attraction or repulsion. And that's important, because if you have two things that attract each other,
They connect.
They connect. And if you have particles connecting with each other, they're not going to create as much pressure, because if I were to hold on to him as he's trying to run into a wall, he's not going to hit the wall with the same pressure. So those two statements are the bedrock that allows us to do the kinetic molecular theory, which you see in our table right here, and we'll talk about in class.
We'll see you in class.
Take care.